This is a fourth tutorial on using Abaqus to perform finite element analysis. We're analyzing the table shown in the figure. It consists of three parts. It's got the table top, a rear support, C channel at the back, and then a wire or beam frame. This tutorial is focused on troubleshooting problems with analysis. So the prior tutorial, tutorial 3, ended with errors in the run. So we're going to start with that here. Go back to the job I just completed, table full. I go to the monitor, and we can see we got the error, too many attempts made for this increment. As I mentioned at the end of that tutorial, that error typically means that Abaqus cannot identify a unique solution to the problem. In other words, it can't identify where all the nodes ended up. That's usually an indication that you've created a dynamic problem rather than a static problem. So you are under constrained. The first thing that you want to do when you see an error like this is go and look for more details in the data that was produced during the run. So in Abaqus Monitor, you can go right to the Warnings tab. And then you want to look through each of the warnings and make sure you understand what they're saying. Because one of these warnings could have told you something initially that led to the eventual error. Okay, so none of these warnings tell me anything that I didn't already know, but there is some other information here. We can go to a data file. The data file is output during the pre-processing phase or the preliminary screening phase of processing your file. So when you click submit, it initially gets checked by Abaqus. This is the check file. So there are some notes in here. But again, I'm not seeing a smoking gun in this file. The message file is the next one you want to check. The message file is output while the solution process is actually proceeding. There is no additional information for me in these outputs. So I move on to the next set of troubleshooting. So I dismiss this tab. The next set of troubleshooting is basically to avoid flying blind. So I've attempted to submit this job and it didn't run. I don't know what the problem is yet. So I can guess and change things, and that is certainly an approach a lot of people use. But my suggestion is to go back to your model and change how you defined it so that everything is tied down somehow, connected in some way. So what I mean by that is the uncertainty, or as I called it, the dynamic state of your system is caused by applying a force to something that wasn't held in place. If instead of applying a force, I apply a fixed displacement, that fixed displacement keeps things from flying apart. So that's what I'm suggesting doing. So let me show you something you can do in the tree. Over here in the model tree, go down to your loads. If you right click on a particular load, you can suppress it there. Suppression means the load no longer will act in the analysis, but it's still saved here if I want to add it again later. I'm going to look at the boundary conditions as well. I've got this edge support, which at the moment is misnamed because it's now referring to the boundary conditions at the bottom there. I'm going to edit that boundary condition just by double clicking it. And you can see right now all that I have specified on those 4 points is just the vertical direction. To make sure this is totally tied down, I'm going to add in the X and the Y direction. So now this frame, which is one part, cannot move because I've tied all the points in. It could deflect, but it can't run away from me. So that takes care of the frame. The channel that's back here, there's a C channel attached on the back edge here. And the tabletop ran just fine in a prior analysis, so I'm comfortable with that interaction. So what I do need to do, though, is change how I'm holding the tabletop to prevent it from running away from me. For that, I need a new boundary condition. I'm going to replace the point load that I added here. I'm going to replace it with a fixed displacement. So I'm going to have a edge force boundary condition. I'm going to always switch to displacement rotation because then I can choose everything on my own. And I'm going to apply that to this point that used to have the force applied. And then I'm going to specify that at this point, I'm going to set all of my displacements and rotations. The rotations are important to apply here as well because I don't want this to free spin about any axis. I'm going to set them all equal to 0, except for the 3 direction, so the downward direction. And I want to apply a fixed displacement there. I'm going to have it move down 2.5 inches, which is about what the table deflected in my last analysis, the tabletop. So this hopefully will produce a similar deformation field, and we can see what happens at this interaction, because I suspect that's where my error is. Okay, so now I've added that edge support. Okay, so with only that one change, I'm going to go back to job, or 2 changes. I'm going to go back to the job module and submit my job and see if I made anything better. This time, the analysis completed successfully. You can see it lists down here. It did a full step. There's no errors this time. So that's what I was hoping for. This is not the same analysis now. I've changed it by applying a fixed boundary condition and perhaps over-constraining things. But this at least allows me to see what's going on, what's not working properly. So I now can click on results. Such an odd orientation it gives me. Okay, so there's my table, and I look at deflection. Okay, deflection looks pretty good. All right, actually, it appears that the contact is working out just fine. That was what I thought was the problem. So in fact, this analysis looks like what I would expect. Let's go back to the interaction module. So I have an interaction, which is the top to the frame. That's the contact here. That appeared to be working just fine in that result. So I don't need to change the interaction. And I don't need any other interactions. Remember, if you can remember from the last analysis, what I said is that at the 2 corners of the frame here, there will be pins holding the tabletop to the frame. And then at the back edges here, there will be constraints that will hold them together. So let's look at what I've got for constraints. So what I did is I forgot to add the constraint that ties the back edge of my tabletop to the back corner of my frame. So let's add a tie that will tie those together. And it's a tie constraint. Continue. Now I'm going to use nodal regions because I want to take this back edge of the tabletop and I'm going to connect it just to this point at this corner and then the point back there. So I'll use a node region. For the master nodes, I'm going to go ahead and grab the edge of the table there, hold down shift, grab this edge. That's my master line. And then for the slave, I'm going to do a node region as well and do just the point right there. Hold down shift to do the other point. Okay, now I've got those 2 together. We call them surfaces even though they are nodal regions. I'm going to use computed default. I'm not going to adjust save surface initial position. And I think I do not want to tie rotational degrees of freedom. I want this to be free to rotate at that point because my magnets are not that fixed. Okay. So now, just to verify I haven't caused any new problems, I'm going to submit this again. Okay, so I caused a problem. So let's check out another option. Check the mesh size. These are all things that can contribute. I've already looked at the material, so I'm going to look at the mesh size. And one thing I notice here is that this point and that point are pretty far apart. It's possible that my tie constraint isn't working quite the way I want it to because the nodes are too far apart. So I'm going to remesh each of these components at half of the existing size, and let's see if that improves anything. So double the mesh size here. You can see that aligns pretty nicely with this end now. So hopefully that would improve things. Let me go ahead and do the same decreased mesh size on the other 2 parts. I have to switch over to part for those 2 because they were dependent instances when I created them. Okay, so now I've got everything remeshed. Let's go back to the job module and try submitting again. So that solved the problem. Okay, let's go verify the results. Again, I'm happy with the shape of things. So this is based on a fixed displacement. I've now got my ties at the back corners here that I wanted. So now let's see with that smaller mesh size if I can go back and add my load and get rid of that extra fixed boundary condition. So I resume the load, and under boundary conditions I suppress the edge load and I try to submit it again. So it's a process of redoing what we undid previously. Okay, success. We are still running okay. We'll take a quick look at the results, make sure they still look reasonable. Yes, deformation still looks good. In fact, let's get the numerical value for that deformation. 2.9, almost 3 inches of deflection. This is an interesting rainbow pattern we've produced here. You can see we're going downward, but then upward on this point. This is because we're looking at the magnitude. If I switch it over to U3, we can see we're negative and positive. So the rear edge of the table does actually move up under this extreme loading condition, as I suspected it would, and that allows the stresses to be more reasonable. Okay, so things are running well. There's one other thing that I added in order to get it to run that we need to undo, and that was adjusting the floor. I fixed all of these in all directions. I want to get rid of the fixing in the X and the Y, allow it to slip around a little bit. This might cause it to go unstable again, in which case I'll grab one of the corners and just have it held in place. But let's see if I can do it without holding any of them. Well, we got a little bit more warning information up here. It was getting unstable, but no, it did not. It was not able to run with no constraint there. So let me go back, and instead of fixing all 4 of those points, I'm just going to grab one of the points and fix it. Okay, that was sufficient to get us to run. Again, overall, shapes what we would expect. The next step that I would do if I were to continue this analysis is I would look at what the proper constraint is at this end of the table and frame interface. But overall, I think this shows you the process of going through the debugging. Let me give you a quick summary here of what the steps were that we went through. So just real quick here, these are the steps that I recommend for debugging. First off, make sure you review all the warnings that Abaqus gives to you. Then read any notes that are in the data and message files. Sometimes you can learn something there. Third, find some way to get the analysis to run so you can look at physically what's happening. So don't fly blind, tie everything down. You do that by editing the boundary conditions on each of your parts so that they can't move, and also replacing any forces with fixed displacements, at least one set of complete fixed displacements so your parts can't move around. Then you want to go through and manually check each of your boundary conditions, each of your constraints, your interfaces. All of that, if you've completed all that and things are still not running well, you do what we did here and you check your mesh sizes. In particular, you usually want to decrease those mesh sizes. Sometimes that can fix the problem. And then finally check your materials, or perhaps the thicknesses of parts, because if things get really weak, they can also cause this sort of error in the system. If all of this fails, then you need to go get some additional help from someone. Okay, that wraps up this tutorial on how to approach debugging in Abaqus. Good luck.